Okay, I started recording. Good evening. Welcome, everybody. We're going to start today talking about serial communication, which is chapter 10. And let me put this away. Noisy. In your case, this semester, the chapter is for your information and benefit. It's not going to be part of the exam, okay? And I'm gonna try to make it as simple as possible. I'm gonna stay very high level, but then I'm gonna do a demo and make our microcontroller talk with the PC, okay, serially. But I'm not gonna go very deep, and I don't want to take 2-3 hours more than like last time. My expectation wasn't very accurate. So serial communication. Well, let's start with the slides. Easier. Serial communication is a way to communicate. Serial versus parallel, right? You remember we had parallel ports? Well, I don't like slides. Just, okay. So let me start it this way. So if we have a microcontroller 1, okay, a 16F877A, and microcontroller 2, also 16F877A, and it could be anything else, right? And this controller has a byte that wants to transmit it, send it to this controller and put it in a memory location that will be able to hold a byte. There are two options to send this byte. And you can send it all the byte, the 8-bit. We can send them in one shot. And we call this parallel communication. So we can get port B, port B 0, 1, up to port B 7, and here the same, port B 0, port B 1, up to port B 7, and connect them together. So write the byte. So take this byte. If it's in memory location, get it. Well, you can just say port B and C, port B equals the byte, right? Then the byte will be written here. If it was 1110, everything 0, so we'll get the 111, then everything zeros. Then they will be here 111. So you set these ports as input on this controller and output at this controller. But there should be a way to communicate. So this knows that I wrote the byte on the pins. So we can use another pin to trigger an interrupt, مثلا, to tell it, oh, I sent the byte, it's in the pins, go read it. And you go read it and put it here, right? So we send them in one shot. This is called parallel. Another way to do it is serial or serially, serial communication. So instead of sending this byte in one shot, let me draw the drawing again. So the first microcontroller, second microcontroller. And again, this time I'm going to use just port B 0 alone. Port B 0 alone here. And I'm going to put the byte in this controller, put it in port B, and then I'm going to start doing this. Port B equals port B shift to the right one time, then some delay, then do this again. 8 times in the loop, 8 times. What does this do? It will get the byte 1, 2, 3, 4, 1, 2, 3, 4 bits. It's true that all the 8 bits are on port B here, but the only one connected to the other microcontroller is port B0. So this will see the first bit. After the shift, it will see the first bit will become here and it will be on port B0 and read it. Then after the second shift, third shift, so it's a shift register, right? A register. I write into it 8 bits once, right? 1, 2, 3, 4, 1, 2, 3, 4. Then start shifting out bit by bit, and some time between the bits. Now, how will this controller know that I sent the first bit? And when did I start? What's the second bit? When is the third bit going to come? Okay, this communication control is called the protocol. Okay, so for us, we can do parallel communication with the tools that we have right now with the interrupts. We can do serial communication with the tools we have right now with the interrupts. But our microcontroller already has something for us that is ready, a place where you can write your byte, a place where you can configure the timing, how fast the shift is going to happen, and you do it on the other controller. So they start communicating with each other using the same rules, the same language that they understand. So you won't have to put extra effort in teaching this the language of communication and teaching the other one of language communication. Okay, so this is the basic, very basic principle of serial communication, is that you have data and you start sending it bit by bit, serially, one after another. Okay. So when we talk about serial communication, and again, I'm saying we're going to do it really fast. There are 2 types of serial communication: synchronous serial communication and asynchronous serial communication. What is the difference? Simple. We know that this microcontroller, this one, where is it? These two are going to be talking with each other. This one has a clock source, right? And this one has a clock source. If the clock source governing the transmission rate, we call it the baud rate, 2 bits per second, 10 bits per second, 1,000 bits per second, 1 kilobits per second. This is something we call the bits per second. Bits per second. We call it the baud rate. This is 9,600 bits per second. So you go set the baud rate here to 9,600 bits per second. You do the same here. Okay. The clock that governs this speed, if it is common for both, and it gives the shift register, the clock source here, is the same one that gives the shift register that is shifting in the bits one by one. If it's the same, we call this synchronous communication. Okay. If everyone has a separate clock, this has a clock source 1, this has a clock source 2, we call this asynchronous communication. Asynchronous. They're not synchronized through a direct clock. They're synchronized using other methods. Okay. So this is the main difference. In synchronous serial communication, there is a single clock, one clock that controls the speed of both the transmitter and receiver. In asynchronous communication, there is no common clock. The synchronization, their agreement on the speed and what bit we are I am sending and you are receiving at this moment is not controlled through the clock. Okay, it's controlled through other methods, and I'm going to talk about it. However, when we talk about serial communication, there are many synchronous serial communication. There are several protocols. So when we say serial communication, there is a way, there are rules. So you write the byte here, then you trigger me, you inform me that you're going to start transmitting, and then I start receiving. And this fast, okay, there are rules. So you cannot be speaking English and I'm speaking Arabic. We don't understand. There is no protocol between us. We cannot understand our language, right? You studied networks, but if we agree, even if we don't know our spoken language, we can agree. Okay, if we meet, we can shake hands. Then we can, shake heads, whatever. A protocol that governs this communication. These protocols, there are several kinds of protocols. Some two famous synchronous communication protocols, serial synchronous communication protocols, called SPI, serial peripheral interface. And the company who called serial peripheral interface is Motorola, and now then later moved to Freescale, and National Instruments also did invent this same protocol almost at the same time, but they called it at that time microwire protocol. And there is another protocol called inter-integrated circuits, a way to make circuits to talk to each other, I2C. So you can buy a sensor, buy a device, the way you can communicate with it through I2C or SPI, okay? These are called synchronous serial communication. The asynchronous serial communication, there are also other protocols. In this chapter, I am going to concentrate on asynchronous, okay? And we're going to do practical exam on asynchronous because it's the most famous, most common, and widely used. So when you send data through your serial port, you send it asynchronous, okay? When you send data through Bluetooth, you send it asynchronous, and so on. So this is the most common type of serial communication. So we're going to learn about it more and do some examples and hands-on and practice it. This illustrates two systems of memory. One that has parallel data and address buses. The other has serial and address and data bus. See how small you can scale down the number of pins. These are terminology widely used. So the rules that govern the communication are called protocols, okay, in the serial world. The device that sends data is called the transmitter. The device that receives data is called the receiver, okay. This controller we are using, the 16F877A controller, has two serial ports, okay. One of them is called MSSP, stands for Master Synchronous Serial Port, and it is a synchronous port, okay? So we're not going to deal with it. The other port is the USART, number 2. The USART stands for Universal Synchronous Asynchronous Receiver Transmitter. This can work either in synchronous mode or asynchronous mode. We're going to use it, but in the asynchronous mode, okay? Basically, how does communication happen in synchronous basics? For example, you have an 8-bit register. This is a register. You write the 8 bits into it, right? Then you provide a clock with a certain speed. On every rising edge, this will shift the input to the output, this input to the output, this input to the output, and what was here is going to go out. And you connect this to the other microcontroller that is receiving, right? So 8 clocks, 8 shifts, the byte that was here is now here. Okay, this is a generic block diagram. You write into a register. A register is what? A memory location now in our case, right? A special function register. You write the 8 bits here. You provide the clock with a certain speed on every rising edge. The bit here is going to go to the serial out. And at the same thing, if you have a pin connected here, what's on the pin is going to be shifted in. So if we have two registers, 1, 2, and we have the same clock source ticking here and here, on every rising edge, the bit that was here is going to move to here. The bit that was here is going to move to here. The bit here is going to move to here. The bit that was here is going to move to the out, the external line. The line is going to be shifted to this most significant bit. So two nodes, a device that is connected to a serial through a serial link is called a node sometimes. Okay, so this is for example a transmitter. It's sent after 8 clicks, the 8 ticks of the clock, the 8 bits that were here are going to be here. Also, the 8 bits that were here are going to come and be here. So it's like a 16-bit virtual shift register, but part of it, 8-bit, is in device 1, node 1, and the other 8 are in node 2. The easy thing here, so you have a serial data out pin, serial data in pin, the things you're shifting in, the serial data out, the things you're shifting out, and a clock source. So if two controllers are going to talk with each other, microcontroller 1 and 2, you need to connect how many lines between them to be able to speak. Serial data out, you connect it to serial data in over here, then serial data in, and this direction is this way, serial data in will be connected to serial data out here. Then you have the clock, which is part of one of them. In this case, the one who owns the clock, we call him a master, and the other is a slave, because he controls the speed, the clock, and everything. Also, since you're sending voltage levels here, these are reference to the ground of this controller. So you need to connect a ground, a common ground as well. So 4 lines. To make 2 devices talk, you need to send them, connect them. For asynchronous, you have 2 clocks, one controlling the shift speed here and another one controlling the shift speed here. But the communication protocol is different in this case. So we mentioned synchronous serial communication. 2 famous companies, National Instruments and Motorola, both invented a protocol called, Motorola called it SPI, Serial Peripheral Interface. National Instruments called it microwire. These are famous. And another one is I2C, is also another protocol that is well known and used in synchronous serial communication. This is how it looks. You have the master, microcontroller 1, the slave, serial data out, connected to pin serial data in. Serial data out is, so the shift here is this way, right? The shift is this way. A clock generator on every rising edge, one bit is shifted out. The same clock will trigger this to shift in something here. So the bit is going to be here. The bit here is going to go out to be received here. Okay. The ground is not here, but this is needless to say. If you're sending any voltage level here, it's a reference to this ground, so you need to share it with the other one. So this is a typical serial communication, synchronous serial communication configuration. Master, slave. You can have more than one slave. So in this case, if you want to talk with this one, you do slave select. You have 3 lines here. You write 100. So this one is selected, enabled. So everything you send out is received by the serial data in here. If you want to send it to this one, you do this one, this byte. This select will be 1, and everything else. Use slave select, slave select. I'm sending you data. Okay. MSSP, it supports microwire SPI. It has its configuration registers. I'm not going to cover it in this lecture, but it's not hard to go and read these registers and look what's inside them. Okay, and learn how to program them. Synchronous serial communication has some limitations. Some of these limitations, like in SPI or microwire, you cannot have more than one master. It's only one master and multiple slaves. The master is the one that can send and decide. You cannot have two masters. And there is no addressing. Only the select. You select one and you send them. Okay, it's not like you send an address. Okay. The slave, when it receives the data, there is no mechanism to acknowledge that, oh, I received your byte. Thank you. Okay, and they're not very flexible. It's not easy to add more devices. These are some limitations of synchronous serial communication. Okay, and they will require an extra line. Because we have a common clock, you need to send another line, a line for serial data out, and a line for serial data in, and this should be this should be enough for an asynchronous serial communication. But since it's synchronous, you send the clock as well. Okay, so extra wiring. The bandwidth of the clock limits the bandwidth of the transmission will be half of the bandwidth of the frequency of the clock. Over long distances, a clock may drift and you can lose synchronization. Okay, these are some limitations. So I put a star for you here. This is what I'm going to concentrate on, the asynchronous serial communication. When two devices want to speak with each other, communicate with each other using asynchronous serial communication, okay, you have a transmit pin, you connect it with the receive pin on the other side, a receive pin, you connect it with the transmit on the other side. That's it. You don't need to do a clock. طيب, how do they know, this receiver, when it's receiving, how does it know that I am receiving 10 bits per second or 5 bits per second? Because it's it's not the same. So they need to predetermine the clock speed. Everyone has his own clock, but the data rate, the baud rate, we call it, should be defined before they start communicating. Okay. And the format of the data when we send it should have a common framed, arranged in a certain way. Before you start sending bit, then another bit, the duration when you send the bit, I send the 1. Okay, how long am I going to keep the 1 before I send the following 0? How long I'm going to keep the 0 before I send the other bit? Then how many bits I'm going to send? 8 bits. Okay, how do I know that I ended the 8 bits? When do I start? There are start bits, stop bits. Okay, so this is how the protocol works to overcome to compensate for the common clock that we don't have anymore. So this is a standard. We call it RS-232, very, very common in synchronous serial communication. Usually the line is pulled to idle, and then these are logical levels. Sometimes they can be flipped. This high could be in voltage, low voltage, and the low is high voltage. Okay, so you don't care about it for now here. So usually you have a pin. In our microcontroller, in the 16F877A controller, we have 2 pins, port C7 and port C6. We use port C6 for receiving, for transmitting data. Port C7 is used for receiving data. Okay, so this is shared with port C parallel port. So when we connect a microcontroller with another microcontroller, if we have, let me do it quick. we do a cross connection. Why do they call it a cross connection? Because if you have a 16F877A and another 16F877A, we have port C6, and port C7. And here we have port C6 and port C7. When we connect them, we connect port C7 with port C6 and port C7 from this side with port C6 in this side. Because 6 is transmit, it should be received by the receive pin. This is the transmit here, and this is the receive here. You transmit from here, you receive at this side, right? If you transmit from here, you receive here. So it looks like a cross. They call it a cross connection. Okay? So usually, when do you start transmitting? Before you start transmitting, the transmission line is an output. There is a voltage here. There is an ideal value of the voltage, okay? It stays as is. When you want to start transmitting, the ideal value will go down, and we call this a start bit. Okay? After the start bit, the time that the start bit is going to stay on the line, and for مثلا 1 millisecond, you're going to stay here low for 1 millisecond. After that, and this got notified, this falling edge would probably trigger the hardware and made it wake up and start counting. Okay. Then you start sending the 8 bits. مثلا the 8 bits were, if I'm sending 1101 1100, this is a byte I want to send. How do you send it? You send the least significant bits first, صح? Because it's just shift register. You shift them out. You send this one first. So 0. Then you send the other 0. Then you send the 1. And they stay on the line for a certain amount of time that both controllers know. Then you send another 1. Then you send another 1. Then you send the 0. Then a 1. Then another 1. Then you stop. You send the stop bit. And the stop bit, okay, I'm sorry. The last one. The start bit is always the opposite of the ideal. Okay? And the stop bit is the ideal. So after you're done, 1, 2, so how many bits did we start? 1, 2, 3, 4, 5, 6, 7, 8. Then now the 9th is what? I'm trying to get something out of my way. Now this is the stop bit. After the certain amount of time, it stays there for a certain amount of time. If you want to send another byte, byte 2, you do another start, and you do again. If you're not sending anything, you stay at the ideal. Okay? Look, did you notice that this byte is flipped in a way when you look at it serially? And here we have 0, 0, 1, 1, 1, 0, 1, 1, so? But this is with time domain. This is position, right? Because you take 1, you send it first. The second byte, second. So it would look like if you put this, if you take this port C6 and tie it to a scope in the lab when you go back, inshallah, you will see something like this: 0, 0, 1, 1, 1, 1, and so on. Okay. So you have the ideal line, start bit, then 8 bits, 1, 2. This means high or low. You don't know what we're sending, right? 3, 4, 5, 6, 7, 8. And there is an option to have a 9th bit. And this 9th bit, we can use it as a data bit, or a parity bit. Parity bit. What does parity mean? If you forgot, you studied parity in digital logic when you were in 2nd year or 1st year. Okay. Even parity, great. So
yes.
if the number of ones I'm sending here is odd, and even I'm using odd parity, both sides should agree on it. If you're using odd parity, so we count the number of ones here, they're even, then this one should be a 1, right? To make them all together odd. If they were odd, yes, then this is a even. For error detection, right? Error detection. طيب. This describes what we said right now. The timing, see this start bit, this first bit, second bit, third bit, stays on the line for a certain amount of time. This time is several clocks. يعني هنا, this is zoom in. Okay, this is the clock, the receiver clock generator, and the transmitter has another clock, and this clock could vary from 10 to 20 clock pulses. Okay, so you are about, let's say 20 times slower than your original clock. So asynchronous serial communication, synchronous, asynchronous, is much slower than synchronous serial communication. طيب. It is slower because in synchronous, you said for every 2 clocks you send the bits, right? Half. Here it is 20 times. You need to write the bit and keep it on the line for a long time, because there is no direct clock between the 2 machines talking to each other that makes sure that they are at same exact moment. So the receiver, when it detects a start bit, it counts, okay, 20 times. Then afterwards, it knows that the first bit is going to come. Okay, it takes samples. It takes a sample after the 3rd clock, a sample after 7th clock, a sample after 15 clock, and averages the samples, or looks at the majority. If they were high, it will consider the bit that it received the high. If they were low, it will consider it as low. So it's much slower, but it saves resources, right? And usually, because you're not sending a clock between the 2 devices, you can connect 2 devices in asynchronous mode. Asynchronous mode. This line could go up to 100 meters. While in synchronous, we're talking about centimeters, meter maximum. Because the clock, after a certain length, it's going to start losing synchronization. You cannot keep sending at that very high speed. Okay. طيب. Now we're going to start with the port, the serial communication port we're going to use actually here. And well, I anticipate, inshallah, in less than 30 minutes we finish and we do a good example. The port we're going to use in the 16F877A controller is called a USART, universal. It is universal. That's the beauty about it. It is universal. You get a PIC, you get a Freescale, you get a PC. This port is universal. Everybody will understand how to communicate with it. Okay. It is universal, synchronous, asynchronous, receiver, transmitter. So you can use it in the mode of synchronous or asynchronous. You can receive and transmit data using it. Okay. And it is addressable, which means the data, the byte you send, could be considered as an address. And I'll point to that. It's not any widely used, this addressing in serial communication, because usually serial communication is used for peer-to-peer communication. This is usually serial. So microcontroller 1 talks with microcontroller 2. So transmitter connected to receiver pin connected to transmitter pin. That's it, okay? Sometimes you can have more. Okay, and what you send here is called an address. So this will wake up if the address was its address, and then the following byte it will take it, the other one will discard it, and so on. But when we talk about networking in embedded systems, there are common networks. One is called the CAN network, where there's a CAN high, CAN low, CAN high, CAN low, and we cover this topic in the graduate level. And this is the network used in all the vehicles today, cars, in your cars. There are up to 100 or more sometimes. It's usually between 60 to 150 controllers. They are all connected through a network. You call it a CAN network. And when you connect your OBD, when you go to the service shop or you have a check engine, you go connect the OBD. The OBD actually is connected to the CAN bus, and it reads here, it sniffs the messages here, and depending on the message it reads, the message ID, it knows what is the fault. Anyways, it's not our topic. So serial communication is not intended for networking, okay? It is to communicate between one to one usually. Sometimes you can have more than one, but if you want to do a network, there are other ways. It's not using the USART. Okay, in our controller, as I said, okay, you can make your controller work in full duplex or half duplex mode. When we talk about communication, we know that we have full duplex, right? Half duplex. And simplex, right? Mode. And you're aware of these? So a phone transmitter, receiver, yeah. So if two entities are communicating with each other, and at the same moment they are able to send and receive. When I'm talking with you on a phone, I'm talking and I can be listening, right, at the same moment. This is a full duplex, okay? A radio device or a walkie-talkie that you all know about is considered a half duplex. There is no two lines. You're either transmitting or receiving on the same line, okay? They call it half duplex. You can transmit or receive, but not at the same time. You need to stop transmitting if you want to receive, and so on. Simplex, you only receive, right? One way, like a receiver radio receiver. Our microcontroller can work in full duplex because we have one pin for the transmission and another pin for receiving. You can be transmitting at the same time you are receiving, okay? And this has supporting registers and clock. This has supporting registers, and the clock will be feeding both of them. You can be doing the same at the same moment. So we can make our controller work in this mode, being in the mode of transmitting data to some device and in parallel receiving other data from another device. The pins that we use here are shared with port C. Bit 7 is used for receiving, and bit 6 is used for transmitting. The registers we're going to use, the most two generic register, TX-STA, RC-STA, transmit, STA, receive, STA registers. طيب. And when you look inside them, we will learn what each bit inside them, how to enable them, how to configure the clock speed, and all these things. So these are the registers. Well, good timing. طيب. This is the transmit. See, it's hidden. It's 98. It's address 98 in data memory, and it's a special function register called TX-STA. طيب, let me just larger the screen. Bit 0, this one, is the 9th bit of transmitting data when we transmit. Yani this USART, the USART, when we USART, when we configure it, we can configure it to send 8 bits, 8-bit data, or 9-bit data. 8-bit or 9-bit. If you want to send 8-bit, there is one register for the data, okay? Call it a transmit register. If you want to send 9-bit, that register only holds 8-bit. Where will you put the 9th data bit? You put it here. You put it here, okay? So this is a data bit. If you choose to use 9-bit data communication. If you don't use 9-bit, this would be the parity bit. طيب. Bit number 1 here is called the transmit shift register status bit. Transmit shift register status bit. So when you write your data to the data register, transmit data register, the content, you write your 8-bit, your byte, okay? We send the byte by byte, yani 8-bit. This will be moved to a shift register. And it will start shifting the bits one by one on port C6, okay? So when you want to transmit a byte, you write it here, it automatically sent to the shift register and starts shifting, okay, transmitting. Now, whenever this shift register has data in it, you cannot transmit anything new, صح? You cannot write another byte because you're going to interrupt the previous byte. Because it's not a one shot. You write the byte in this register in parallel, right? But when it's moved here, it starts sending out in serial. So slower, much slower. So when this shift register is busy, it's full, you cannot transmit a byte. You need to wait for it to empty, then you send the next byte. When it's empty, you send the 3rd byte. When it's empty, you send the 4th byte. How do you know it's empty? There's a bit here, this bit. When this bit becomes a 1, then it's empty. It's clear to send another byte. If it's full, you read a 0 here. This is bit 1. So if we're not going to use interrupts, this is a bit that we will be waiting for. While we say, in our code, we will say, while this bit is not 1, keep waiting. When it's 1, start moving, transmit the other byte. Okay? That's how we're going to do it. This bit, high baud rate select bit. It has to do with the baud rate. What is baud rate? It's the number of bits per second that you transmit. There is an equation to compute the baud rate. We're going to come to it later. And there is there are 2 equations actually. High and low baud rate. High speed or low speed. And we're using the asynchronous mode. So we set this bit to 0 and 1, and depending on what we set it to 1 or 0, the equation that we're going to use is going to change. I'll remind you about it when we get there. For synchronous, this is, if you are doing synchronous communication, this is not used. This bit is not implemented. This bit decides that we are going to use the USART in the synchronous mode or asynchronous mode. So in our case, this is always going to be 0. Because we're going to use the asynchronous mode. Synchronous or asynchronous? We're going to do asynchronous. To enable the transmitter, power it up, everything. This is the enable, transmit enable. So you need to write a 1 here. Bit number 5. Enable, disable. The number of data bits we're going to send. Are we going to transmit 9 bits or 8 bits? Usually it's 8. So this is all, usually, most of the time, we're going to be 0. If you choose 9 bits, your 9 bits, you write the first lower 8-bit in the transmit 8-bit data bits register. The 9th bit will be written here. the most significant bit is not used in our case in asynchronous mode. طيب. One more register to go, which is the receive register. Yeah. RCSTA, and it is bit 18, special function register. Okay. The bits here bit 0 is hidden. 9th bit of received data. Okay. When you send 9 bits, you receive 9 bits, صح? So the first 8 bits are put in a register called the receive register. It can hold up to 8 bits. Type the 9th bit, where is it? Is going to be put here. طيب, let me start here. Bit 7, serial port enable bit. طيب, serial port enabled. So the whole serial port, you enable it by writing a 1. طيب, what is the enable we saw over here? Is the transmit. So this will enable the receive alone. To enable the transmit, you need to do the other bit as well. طيب. This is also on your, if you are receiving some data, are you receiving 9-bit or 8-bit? That was for the transmission. So 8-bit, you make this a 0. Single receive enable bit. In the asynchronous mode, this is not used. Bit 4, continuous receive enable bit. Asynchronous, 1 for enable, 0 for disable. When you receive, are you gonna keep receiving continuous, or you want to receive once and stop? You decide this, 1 or 0. Address detect enable bit. This is bit 3, this one. This bit in asynchronous mode, if it's 1, it enables address detection, enables interrupt, and load the receive buffer when RSR8 is set. Yani, in this case, the receive 9th bit, data bit, if it's 1, and if you would need to choose to transmit a 9 bits. The 9th bit is the parity bit. If it's 1, the rest of the 8 bits will be treated as an address. Okay? So the receiver will wake up on an address if it was its address and work. And then when it's done, it will go back to what it was doing before. Frame error. This is a flag that raises if the frame has any errors. Yani, you know the frame, what is the frame? We have a start bit. We have 8 bits. Okay, we have a stop bit, start, idle. If this frame has any issues, for example, you did not count 8 bits. The timing is wrong. I didn't see a stop bit. An error flag is raised called frame error, because this could happen because you don't have a common clock between the transmitter and receiver. Overrun error. If you are receiving data faster than that you are able to take from your shift register and put, okay, the shift register receiving data faster than it can shift in, the data you're reading is overwritten, right? Overrun. So you get an error. It will tell you. So these are our registers. This is quick. I'm not going to go detail. So there's a register called transmit register. So the registers we're going to use here, guys, are TXSTA. This controls transmission. RCSTA controls receiving. Okay, this one is called TXSTA. TX register, sorry, TX reg. TX register. This is where we write our byte to be transmitted. طيب. And automatically it will be moved to the shift register and start sending it out. So when we want to send something, we write it here. طيب. But we need to check if the shift register is empty or not. And for the receiving part, the register is called RC register. Let me write them all down here. RC register. When you receive a byte, you'll find it in this register. These are data. The data you transmit, you write it here. The data you receive, you find it here. طيب. So this is a data bus. This is a special function register. In your data memory RAM, you write what you want to send. It transmits, if this is empty, to this transmit register. It adds a start bit, a stop bit, least significant bit, a 9th bit even, if you want a 9th bit, and starts shifting things out on RC8. Okay, this is the transmit shift register status bit, that it is empty or not. This is the enable bit. These are in the control register. طيب. If you enable transmission interrupt, transmit interrupt, when this is transmitted to here, you can raise an interrupt flag and enable an interrupt and take you to an interrupt service routine that you know that you're done sending the 1 byte. Okay. This is the clock generator for the transmitter. This is the bit we talked about to here. Okay, that chooses the formula or that will compute the baud rate. Okay, so there is a register. We need to write a value in it to compute the baud rate. I'll come to it. For you as an embedded system programmer, all what you need to do is to be able to write to this register. It will shift everything, enable everything. It will be easier when we write the code. Okay. When you compute the bit, the baud rate, when we set the transmitter here, TXSTA, we choose this BRGH, which is the baud rate high select bit. We can use high speed or low speed. If this bit is 1, if we write this bit 2, 0, 1, 2, if you write it 1 or 0, this means you are selecting this bit, this formula, sorry, or this formula to compute the baud rate. طيب. Now, when I want to set up the two controllers to talk with each other, I say I want them both to talk with a speed, with a baud rate of 9,600 bits per second. طيب. 9,600 bits per second. طيب. So this is a known value. This is a known for us. Known. The unknown is a register value we need to compute, which is this SPBRG, or this. طيب. So this is a register. We need to write it. The value we write here will decide the baud rate. So when I say I want a 9,600 bit per second, I need to apply this formula and figure out what this would be. We'll do an example, and it depends on your oscillator clock in 2 cases. We call this the high speed and this low speed, because you can get higher baud rates here, because here in the denominator, you see we're multiplying by 16, right? Here we're multiplying by 64. So the number overall, if everything else is constant, the number you will get from here is lower, right? So you get lower baud rates from this one. If you apply this one, you get higher baud rates. This is in asynchronous. In synchronous, it's not used. For example, this is an example. We say I want. This is what I did. Yani let me clear. Kharabish. I want this to be 9600 using high speed. What do? I need to compute this value. What is this value? This value will be the ASPB RG register will equal the oscillator clock, right? Which is in our case 8 megahertz divided by 16 times baud rate goes down 9600, right? And all of this minus 1. The value will be, I did it here, will be 51. You ignore the fractions here, is 51. So you go say, you write in this register 51. Can we use the lower baud rate? Yes, we can. But you need to compute this value. It's going to be different. But in all cases, there is a max, right? Yani the lower value, the lowest value here is a 0, and the maximum value is 255. So the baud rate you can compute here has a range, and this will have a wider range because this is smaller. Right. This is the receiver part. You're receiving data. This is the clock oscillator. You use the baud rate 16 or 64. You set the clock, the shift speed. You're receiving data on port C7. It starts shifting to the shift register. Okay. You're gonna receive more than 8-bit. You're gonna receive the 8-bit if you choose 8-bit or 9. You're gonna receive the start bit and the stop bit. This will be taken out, and the 8-bit data will be moved to the receive register. If you have 9-bit, you'll receive it. It will be put in that bit in the RCSTA register. When you're done, you can enable an interrupt to tell you that you are done. And this is what exactly we're gonna do. We're gonna use interrupts in the receiving mode because it doesn't make sense that you want to receive something from somebody. Somebody sent you some. You go just stand next to the laptop waiting. Did I receive something or not? Right? You do your homekeeping things. When you receive something, you get an interrupt. This is generic. This is a simple example. You can look at it. I'm gonna move to a more complex one example that I worked on yesterday, and I'll explain it. And writing it from scratch, I used to do this, but I don't want to keep you one more hour, okay? But I'll explain it just like last time. Let's start a new project. And this is gonna be class demo 16. Serial communication. Okay, and let me start a notepad to just gather them together, because I had here on the slide to put them into columns, Control A, Control C, to make them fit. So I'll put them underneath each other. Then I copy them and take them to the IDE here. And this is our program. So what we're gonna do, we're gonna configure the transmitter on our microcontroller on the PIC and make it send a message. Say, hello, this is the embedded system class at PSUT Spring 2020. And something underneath. And then it will enter a mode where it will wait for the keyboard, somebody using this laptop, to transmit any character. It will get interrupted when it receives a character. And then it will take this character, add a 1 to it. طبعا before when it receives it, it displays it on the 7-segment display. So whenever between 0 and 9, it will display it on the 7-segment display on the microcontroller. Then it will add a 1 to it and send it back to the laptop. Okay? This is what I'm going to do. So I'm going to use the serial port of my laptop. But if you want to make 2 microcontrollers, I don't have 2 boards and 2 microcontrollers. You can do this, right? If you have 2 microcontrollers that you want this one to send the message to this one, all what you do is you take port C6, connect it to port C7, and port C6 from the other side, connect it to port C7, take the ground of this one and connect it to the ground of the other one. Then you write a program here, you configure these registers plus the baud rate, and you write another program using these registers right here, and you will have a program running here, a program running here, right? This one will be transmitting, this one will be receiving something, you process it, you send something back, command, whatever. But the baud rate has to be the same for both. In this example, we're going to make this laptop, this controller, talk with a laptop through the USB serial port. In the old days, laptops and computers used to have an RS-232 layout, okay, pin layout, a DB9, they call it. And it has, I think, if I remember well, pins number 2 and 3 were the send, the transmit and receive, and there was one for the ground. And we used to, you use them and connect them to RC6 and RC7 and ground. Today, we don't have them on new laptops, but we have the USB. You can configure a virtual COM port. We call it virtual COM port. You can Google it, virtual COM port. So you get a port called COM1, مثلا, COM2, COM5, whatever, and you use it as a serial port. ماشي? And the USB will convert the signal. Okay, so let's write our program. Oh, well, actually, we wrote it, but let me explain it. So the first line of code here is the 7-segment map, because I'm going to be sending to the microcontroller numbers, right? 0 to 9. So this will need a map. A 0 is a 3F on a 7-segment, 06 is a 1, and so on. We explained this when we talked about 7-segment display. I have a byte here, unsigned character called my receive buffer to put my data in it, and my receive flag, a flag that is initially 0, that raises when I receive something. Then I have a string here. This is a pointer to a string. Star message 1 equals, then I write a string that I want to transmit, another message 2, and I put a dot, a period here at the end, a full stop, and I wait for it. And when I transmitting, when I find that at the dot, I send it and stop sending. Okay, so like a null bit. طيب. Then I define 2 functions. A function to initialize the USART, a function to send the byte through the USART transmit, and I give it the byte I want to send. It doesn't return anything. طيب, how do we receive? I don't have a function for receiving. I do receiving through an interrupt. طيب. So I have an interrupt here. The interrupt, where is it? Starts here. And it's here. أنا عامل هيك شفرات. This is the interrupt. And if you remember the peripheral interrupts when we studied chapter 7, to enable the interrupt first in the main loop, here's the main loop. Where's the main loop? Here's the main loop. Where did we enable the interrupt? Where did we enable the interrupt, Belal? Intcon, where's the intcon register? Intcon. Hey, see? In the initialization, I did it in the initialization. When I initialized the USART, okay, let's do this. I initialized the USART. What did I do? I wrote in this register SPBRG12 to configure the baud rate to 9600. Why did I use 12? Because in the TXSTA I used low speed, so I used the formula, the other one. Yani I wrote in TXSTA 20 hex. Yani what did I do? Let's go to TXSTA. This is TXSTA. Let me clearly. What did I write here? 20 hex. So 0, 0, 1, 0, 0, 0, 0, 0. So what did I do? This is unused. We selected bit 6, 8-bit, 0, 8-bit. Then I enabled the transmitter. This is the one. Then number 4, I asked to use asynchronous mode. So it's a 0. This is unused. Then this bit is a 0, which is the baud rate. I used low speed. So I'm going to use what equation? Oops. What equation? Undo. I used this.
بس ممكن سؤال.
This equation. تفضل يا قيس.
مش البفر هذا ستيتس مش انا بكتب عليه، المفروض فولي يطلع لي، مش انا بكتب عليه فولي.
شو هو؟
البفر او انه اذا هو فاضي ولا مليان، اللي هو البت.
yeah right انت بتقراه، بس انت يعني I did not، يعني اذا مش مقبول للكتابه عليه it's not gonna take it, right? You read it. It's a status bit. You cannot change it.
Yes.
يعني for this bit، يعني انت you're talking about if this was a 1 would it matter? No, it doesn't matter. يعني if it was احنا we wrote 0x 20. If you wrote 0x 22 would it matter? No.
No. تمام.
Okay. طيب we use the low speed. بعدين this is something we read parity bit data we used 8-bit اصلا, so this doesn't matter. طيب so we initialized here. طيب we use the low equation. So this baud rate bit is going to be 12. If you apply it, if you apply it in this equation, we use this upper one, not the lower. If you use the bottom one for this 9600 speed, it will be 51, this register. But we use this one. So the equation will be what? خلينا نحسبها الباud rate. Let me run here. So we use this one. We divide by 64. So it's going to be 8 megahertz. طيب before it's going to be 64 طيب times 9600 equals.
دكتور انت حطيت 6 مش 64.
Okay. Did you know something? طيب انه that you can do math in notepad anyways. طيب يلا. Not time to waste time. Okay, let me do this. So 64 times 9600, and nobody asked me why 9600 every time, but I'm gonna answer this بدون ما حد يسألني. Okay. Then we divide 8 million in this on this number 614,400 8 million اللي هي 8 ميجا هرتز صح؟ تقسيم 614,400 minus 1 شو طلع؟ well 13 كانت minus 1 شو سويت أنا؟ It was 13. The result is 13, right? Minus 1, 12. خلاص بديش أرد أعيدها. 12. So here is where we got the 12 from. ماشي. RCSTA 90. RCSTA is this register. No, this one. 90 hex. So we wrote, how do you write a 90? 1, 0, 0, 1. This is a 9, then zeros, right? So enable serial port, then 8-bit, 0, then 0, don't care, it can be a 1. Then this one, asynchronous, disable continuous receive. I'm going to receive 1 byte by byte. Address enabled is not enabled. And these are status bits, it doesn't care, you read them أصلا. And this, it doesn't care. طيب, this is 90. Port C, we set port C to be 80. ليش 80? Because port C7 the most significant bit TRIC هاي شايفينها. This ايش؟ This sets port C7 as input, port C6 as output. Then I enabled the peripheral interrupt for port C enable interrupt in PIE1. شوفوها. You want to look at it? This was in chapter 7. When we talked about interrupts here. PIE1 port C enable interrupt receive. هيو هون. This bit we made it a 1 here. So what is this number? 2, 0, right? Hey, we ordered with 2, 0. So we made that bit enable. And in the intcon, we wrote a C, global interrupt enable and peripheral interrupt enable. Done. So this is the initialization. The transmit function, we say, while the transmit STA ANDed with, we mask all the bits with 0 except the bit number 1. اللي هو إياه بالترانسميت STA اللي هو الفلاج اللي حكى عنه قيس قبل شوي. If this is true, معناته البت is 1, right? يعني the transmit buffer is full. يعني لا is full ولا empty? Let me check it. Transmit STA هيو. If it's 1, it's empty, يعني 0 full. If it's 1, معناته we're good to go. If it's 1, it's good to go. So هذا true. فأنا حطيت قبليه النوت هاي، صح؟ هاي النوت حطيتها قبل. While not هذا الحكي لما يكون 0 يعني full، وهون في semicolon at the end. يعني get stuck here while this bit is 0. When this bit is 1, the condition will be true and we'll get out of this while. So we take my character, which is the byte I passed through the function, unsigned character, and write it in the transmit register. This is automatically going to be moved to the shift register and start sending it. So these are our 2 main functions. شو هذا؟ طيب المهم. Let's go back. So we enable the interrupts. The interrupt for the receiving So if the interrupt flag another 20 but مش بالPIE 1 بالPIR 1 صح. If the flag is 1 then what got me into this interrupt is the received. I received something on the receive pin. So take the receive register, RC register byte, put it in a buffer that we defined here. يعني unsigned character, my receive buffer, put it here, and raise a flag, a software flag for me. This is the way I thought. And two, you are better programmers than me. I know you can do something better, but this is what I thought of. Okay. So I took the the byte I received, I put it in a memory location, and I raised the flag. And then I cleared the PIR1 interrupt flag for the receive. All initializations are done. What am I doing here in the main for once? I'm setting port D as output عشان أكتب عليه على 7 segment display because the 7 segment display is connected to port D. I'm setting port A to be digital because by default it's analog. So we write in ADCON106 and I said why. It's in the recording of the A to D chapter. TRISA, all bits of port A are A output. And I wrote on the lower 4-bit of port A 4 ones. So I enabled, these are the common cathode pins of the 4 7-segment displays I have on my board. I enable them all together. Then I called the function that will initialize the USART, which writes the transmit register, the receive register, enabling the receive interrupt. Okay, then I want to send the first message. I want to send the stars, then welcome to the class, بعدين the stars again. Okay, so I say while message to bit I, هون بلشت I 0, هي 0. Okay, start from message to character 0. While it's not equals to the dot I put at the end, what do? I transmit USR transmit. This is the function we wrote underneath. I transmit what? The character as is. And it will take the ASCII code of it because I put it in here in the text format, right? So it will send the H, then the E, then the L, then the L, then the O, and so on until it gets to the dot. طيب? So I'm sorry, the stars. It's going to start with the stars because message 2. So it's going to send those stars until it sends first when I is 0, then we increment I, and we stay in this while loop until we get to the dot. طيب? Once we're done, we reset I to 0. We send a character called carriage return and a character called new line. ليش? What are these /R and /N? These make whatever you send afterwards on the screen appear in the bottom. A /N is a new line, but it doesn't start from the first column of the line. So a carriage return is needed. Okay, in short, this will make a new line start, but they are characters. Then I send the other string, which is message 1, the same manner. I is 0. Send the capital H, the E, the hello, and keep on. Get stuck in this loop until you send the first message. But then send the stars again. Okay, then this is the infinite loop. What am I doing in the infinite loop here? هاي initialization function. My infinite loop is easy, by the way. My infinite loop is actually while I am not receiving any receive flag, this bit I set it here. Where? In the interrupt. Hey, my receive flag, I set it to 1. It becomes true in the interrupt when I receive something, when I'm interrupted. Okay. While this bit is not true, I'm just stuck doing nothing. If you want to do anything, you just go ahead and do it. When I receive something, the bit will become a 1. I'll get out of this loop. I reset it. And what I received in my receive buffer in the interrupt, I want to display it on my 7-segment display. But my 7 sigma display displays numbers, right? But what I receive are going to be ASCII codes. So to convert from ASCII to number, you subtract a 30 hex or a 48 decimal. Are you familiar with this?
Yes.
Okay, great. Because I'm going to be sending numbers from my keyboard, from the laptop. When I press a 4 on my laptop, the laptop is going to send a 34 hex. The microcontroller has to subtract a 30 to keep the 4 alone and display it on the 7 sigma display. طيب. Then, whatever I received in my receive buffer, the 34 hex, I add a 1 to it and transmit it again. I send a 35 hex back on the transmit buffer, on the transmit pin, and I will receive it on my laptop. Okay, and I'm gonna send a carriage return and a new line. So what I send back is gonna be underneath each other, not next to each other. So this is the program. خلاص, we're done. So, طيب, my laptop. What is the tool I'm gonna use on my laptop? First of all, let me program this. Okay, في error on. What is this error? I may have done something when copying stuff yesterday, يعني. This is the while. طيب, this is the main, يعني بتكون. This is the main, yes. طيب, this is the init. Close it here. This is a transmit, and we close it here. طيب, what is this then? Let's see what's the problem. Okay. Maybe we can. Oh, we still have another thing. What is this? Bug. So here, interrupt. This is for the F. No. This is for this. This is for the interrupt. Okay. Then we go to the main. Void main. Okay, this while has a 1. This while has a 1. This while has another 1. And the while one has this. I tested it. What is this? So what if I build now? Okay. Just a stupid error. I don't understand what I did. I just deleted and brought it again. Okay, it's programming. Done? Okay, I'm done. So look, guys, look, we're done with the chapter. Let me show you what I'm gonna do. To make this work, in the old days, when are you familiar with Windows XP?
Yes.
Did you use it?
مش لهالدرجة احنا صغار دكتور.
والله ما يعني I lost بصراحة track. Okay. In Windows XP there was a free tool called Hyper Terminal. And I know when we moved to 7 and Absar Shu, the hyper terminal was not there for free anymore. But at that time, I copied these two files from Windows XP, and I have them. It's a hyper terminal, but I'll give you the alternatives now. This is a hyper terminal, a dummy terminal that I want to use as a serial interface to talk with the microcontroller. Okay, let me call it here YY whatever. Okay. And I'm going to use the COM port, COM5. This is the one when I plugged in the USB of the board into my laptop. This is the one that appeared. To make a virtual ports, I went to Google and I searched for virtual COM ports. Virtual COM port setup, whatever. You can find. Yeah, this is the one I think I did. Virtual COM port. You download it, you set it up. Yes. PCP drivers, virtual COM port driver. Okay. I have Windows 10 maybe, I think. I set up the executable. I get the COM ports. Okay. That's it. Okay. Now, this dummy terminal is dummy. Okay. It's not intelligent at all. I'll show you. You need to tell it what to do. First, the baud rate, the bits per second. This has to match the number I set on my microcontroller in the code I just programmed. What did I do over there? 9600, okay? Does this answer something? Why did I always write 9600? Because this is one of the standard numbers that are usually used in serial communication. Would it matter if I tried to set my baud rate on my controller to be 9500? No problem, you can do that. But you need both computers, both microcontroller to be at that speed, 9500, okay? My controller, I know how to do it. On the laptop, I don't know. I have to pick one of these, okay? So I can do 19, 20, 200, 38, 400, these numbers. Okay. How many data bits did I choose? 8, okay, not 9. I did not have a parity bit. I have one stop bit because some serial communication peripherals you can set 1.5 or 2 stop bits. Okay, here we did one one stop bit. We did not do any kind of flow control, so this is none. Okay, apply. Okay, now this is ready. طيب, I'm gonna stop sharing my screen. Well, let me share my screen. خليها, يعني I'm gonna do both, but then I'll run the camera on the other device. I'm gonna write, if you trust me, I'm gonna push the button number 1. Well, لا, قبل ما I need to reset, يعني I programmed my controller, صح? I need to reset it. Oops, what did you see? This is the message we sent over there.
Message, Doctor.
How do I get it? I did the reset on my controller. I'm gonna do another reset. See? Another reset. Every time I push a reset, we send this message and we start over again. Okay? طيب. Now, if you remember the program, we send this message, we send these stars, right? Then the message, then the stars. Then we're stuck waiting to receive a character. I'm gonna send this character from my laptop. I'm gonna push the number 1 on my keyboard. I pushed number 1. What do you see?
2.
2.
ليش؟
لأنه it received it, added a 1 and returned it back, صح? When I push 1, the microcontroller received 31 hex. Plus 1, 32 hex. Send it back, display the ASCII code 32 will be this shape 2, right? Now I'm gonna press number 5. What do you see? 6. Right. I'm gonna stop sharing to show you the other part, the board, okay? So let me stop sharing. Then turn on this camera. Then what? Disconnect the voice from here. Enable the voice over here. Okay. Switch the camera. Okay, what do you see? شايفين يا جماعة? You see my screen?
Yes.
للشاشة.
I'm gonna go back to the hyper terminal. You see the hyper terminal. This is what I shared with you a second ago, right? And this is my finger. I'm gonna press number what? What is this number? 4, huh? 4. What do you see on the screen?
5 عملت لها increment.
What do you see on the 7 signal display?
4.
Okay. Now I'm gonna press 5. What do you see? 5, 6, 7, 8, 9. طيب. Here, what do you see? When I press the 5, you got a 6. When I press a 6, you get a 7. Press a 7, you got an 8. When I press an 8, you got a 9. When I press the 9, you got a character because it's out of the 7 segment range. طيب. طيب. I want to press a small a, small a. What do I see here?
B.
B. Because it doesn't matter. Any ASCII code, I'm adding a 1 to it. Small d. I see here an E. Okay, but what do I see on the 7 segment display? Rubbish, right? A. This is what you see when you display an a B. Okay, because it's a 7 segment display. I did not account for any characters. But here I'm sending them back. Well, I'm sending them back, but you can do your application to send other data, صح? طيب. What I'm doing here using the hyper terminal, so you can use the hyper terminal. I'm gonna disconnect it now. Micro C has a terminal built in it. Here. You see it? This button. Push it. Select COM port. Set the baud rate. Stop bits. You see it, right? Stop bit. 8 bits. Buffer size. Okay. Then you do connect. Now we're connected. Now you can send here. Let me clear everything. I was testing yesterday. I'm gonna reset my microcontroller. شايفين هون? This area is empty. This area is empty. I'm gonna reset my microcontroller. Okay. I received the message, right? طيب. Here, if I want to send, I write here at the top, مثلا 2. I press ascend. Ascend showed the 2 here on the 7 segment display, and it showed the 2 here at the transmit at the top. طيب. But at the bottom, at the receive, what do you see? 3. طيب. I'm gonna go back to my original setting because it's not comfortable holding this. Okay, disconnect so you don't keep the port open. Where's Zoom? Here's Zoom. Okay, I'm gonna go stop. Okay, guys. I'm gonna stop recording. If you have any questions, you can stay. But I'm done. This is basics of serial communication. You can think of any idea how to implement any program. By the way, in the slides, I really used to do this. I used to do with the students in class. We wrote code to read the analog to digital converter, read the value, convert the voltage, send it to MATLAB Simulink, draw the a graph of the voltage, how it's changing with time. I have these examples, and well, we started teaching this in the lab, by the way, so inshallah you're not going to miss it. But I don't know, this semester is really, I don't know, fast or what happened. We did not skip any single class, and with this online mode, utilization is more. I don't know, but why we were not able to finish. Anyways, let me just stop the recording and you can stay if you like. Thank you very much. I hope you enjoyed the course and the class.